Download this code from codegive.com, link in the description below. OK, let's dive deep into AIM controller settings, focusing on Unity's input system and C scripting. This will be a comprehensive tutorial covering the fundamentals, advanced techniques, considerations for different game genres, and code examples to get you controlling a game object with an aiming mechanic. Part 1, Understanding the Foundation, Unity Input System. Before we delve into specific AIM controller configurations, we need a firm grasp of the Unity input system. It's the engine's modern way of handling player input, offering flexibility, rebindability, and cross-platform compatibility. 1.1 Why use the input system? Abstraction decouples input actions from specific input devices, keyboard, mouse, gamepad, etc. You define what the player is doing, example fire, aim, not how they are doing it, example pressing a key, clicking a mouse button. Rebindability allows players to easily customize their controls without requiring code changes. Cross-platform handles input variations across different platforms seamlessly. Event-based responds to input events, presses, releases, movements, in a clean and efficient manner. 1.2 Setting up the input system. 1 Installation *. If you haven't already, install the input system package. Go to Window Package Manager, search for Input System, and install it. 2 Input Action Asset * Create an input action asset. In your project window, right-click, select Create Input Actions. Name it something descriptive like Player Input Actions. 3 Open the Input Action Editor * Double-click the input action asset to open the input action editor. This is where you define your input actions, action maps, and bindings. 1.3 Key concepts, action maps, actions, and bindings. Action maps * Organize your input actions into logical groups or states, example gameplay, UI, menu. You can enable/disable action maps to change the player's control scheme depending on the game state. Actions * represent specific player actions within an action map, example move, jump, fire, aim. Each action can have multiple bindings. Bindings * link an action to a specific input control, example the fire action might be bound to the left mouse button, the gamepad right trigger, or a specific key on the keyboard. 1.4 Creating aim-related actions. In the Input Action Editor, let's create the actions needed for an AIM controller. 1 Action Map * Create an action map named Gameplay, or use an existing one. 2 Aim Action *. Click the plus icon within the Gameplay action map. Name it Aim. Set the action type to button, because aiming is usually a toggleable action. Add a binding, click the plus icon next to aim and choose Add Binding. In the binding properties, click the path field and select the appropriate input control, example mouse/right button for the right mouse button, or a gamepad button. 3 Look Action *. Click the plus icon within the gameplay action map. Name it Look. Set the action type to value and control type to vector 2, because we need to track mouse or analog stick movement. Add a binding, click the plus icon next to Look and choose Add Binding. In the binding properties, click the path field and select the appropriate input control, example mouse/delta for mouse movement, or gamepad/right stick for right stick movement. 4 Save the asset * Click the Save Asset button at the top of the Input Action Editor. Part 2, Basic AIM Controller Script, No Camera Control. Let's start with a simple script that rotates a game object based on the look input. This will lay the foundation before we integrate camera control and more advanced features. Explanation *. 1. Using Unity Engine, and using Unity Engine.input system, import necessary namespaces. 2. Player input actions, a variable to hold an instance of your input action asset script. Unity generates a C class from your input action asset. 3. Header, references, public transform aim target, a public transform variable you'll assign in the inspector. This could be a reticle or any other object you want to point towards. 4. Header, settings, public float rotation speed equals 10f, public float look sensitivity equals 1.0f, public variables for adjusting the rotation speed and input sensitivity. 5. Awake, creates a new instance of player input actions. 6. On enable. Player input actions.gameplay.enable, enables the gameplay action map. The input system only processes input from enabled action maps. Look action equals player input actions.gameplay.look, retrieves the look input action from the input action asset. Player input actions.gameplay.aim.performed plus equals on aim performed, subscribes to the performed event of the aim action. The on aim performed method will be called when the aim button is pressed. Player input actions.gameplay.aim.cancelled plus equals on aim cancelled, subscribes to the cancelled event of the aim action. The on aim cancelled method will be called when the aim button is released. 7. On disable, disables the gameplay action map and unsubscribes from the aim events. It's crucial to disable action maps when they're not needed to prevent unwanted input processing. 8. Update. If, eSiming, return, only process input when eSiming is true. Vector 2 look input equals look action.read value vector 2, this is the key. Read value vector 2, retrieves the current value of the look action. If the player is moving the mouse or right stick, this will be a vector 2 representing the change in position. Look input equals look sensitivity, apply sensitivity. Float rotation x equals look input dot x rotation speed time dot delta time, and float rotation y equals look input dot y rotation speed time dot delta time. Calculate the rotation amounts based on the input values, rotation speed, and time dot delta time, to make the rotation frame rate independent. Transform dot rotate, vector 3 dot up, rotation x, and transform dot rotate, vector 3 dot left, rotation y. Apply the rotations to the transform of the game object the script is attached to. Vector 3 dot up rotates around the y-axis, yaw, and vector 3 dot left rotates around the x-axis, pitch. If, aim target, equals null, aim target dot position equals transform dot position plus transform dot forward 5f, if an aim target is assigned, move it a fixed distance in front of the object. 9. On aim performed, input action dot callback context, this method is called when the aim action is performed, example the right mouse button is pressed. It sets eSiming equals true. 10. On aim cancelled, input action dot callback context, this method is called when the aim action is cancelled, example the right mouse button is released. It sets eSiming equals false. How to use *. 1. Create a new Unity project, or use an existing one. 2. Install the input system package, if you haven't already. 3. Create the player input actions input action asset and configure the gameplay action map, aim action, and look action as described in part 1. 4. Create a new C script named Basic Aim Controller. 5. Copy and paste the code above into the Basic Aim Controller script. 6. Create a 3D object in your scene, example a cube. 7. Attach the basic aim controller script to the cube. 8. Create another 3D object, example a sphere. This will be your aim target. 9. In the inspector for the cube, drag the sphere from the hierarchy into the aim target field of the basic aim controller script. 10. Run the scene. Press the button you bound to the aim action, example the right mouse button. You should now be able to rotate the cube by moving the mouse, and the sphere should follow the rotation. Part 3, Integrating Camera Control, Third-Person Perspective. This section adds camera control to the aim controller. We'll create a simple third-person camera system that orbits around the character and zooms in when aiming. Explanation *. 1. Header, references, public transform camera pivot, public camera player camera. Camera pivot is a transform that the camera will orbit around. Player camera is a direct reference to the camera component in your scene. 2. Header, settings, public float camera distance equals 5f, public float aim camera distance equals 2f, public float camera smooth time equals 0.2f, settings to control the camera distance, aiming camera distance, and smoothing. 3. Late update, used to handle camera movements. Late update runs after update, ensuring that character movements are processed first. 4. Handle camera, this function contains all the camera logic. 5. Inside handle camera, asterisk. Asterisk float target distance equals e-siming. Aim camera distance, chooses the target camera distance based on whether the player is aiming. Asterisk vector 3 target position equals camera pivot dot position, transform dot forward asterisk target distance, calculates the desired camera position behind the character. Asterisk player camera dot transform dot position equals vector 3 dot smooth damp, smoothly moves the camera to the target position using vector 3 dot smooth damp. This provides a nice, natural camera movement. Camera velocity is used internally by smooth damp. Asterisk player camera dot transform dot look at, camera pivot, makes the camera always look at the camera pivot point. How to use asterisk. 1. Create a 3D object, example a cube, in your scene. 2. Create a camera in your scene. 3. Attach the aim controller with camera script to the cube. 4. In the inspector for the cube. Asterisk drag the camera from the hierarchy into the player camera field. Asterisk if the camera pivot is null, the system should generate one as a child of the cube. Asterisk create a new 3D object, example a sphere. This will be your aim target. Asterisk drag the sphere from the hierarchy into the aim target field of the aim controller with camera script. 5. Adjust the camera distance, aim camera distance, and camera smooth time settings in the inspector to get the desired camera behavior. 6. Run the scene. Press the aim button. The camera should zoom in closer to the character. Part 4, Raycasting for accurate aiming. In most games, you'll want to aim at a specific point in the world, not just rotate the character in a direction. Raycasting is the technique used to achieve this. We will now have the aim target always point where your mouse is on the screen. Explanation *. 1. Handle aiming, * this function now contains the aiming logic. 2. Ray equals camera.main.viewport point to ray, new vector 3, 0.5f, 0.5f, 0. Asterisk camera.main.viewport point to ray, new vector 3, 0.5f, 0.5f, 0, creates a ray that starts at the camera and goes through the center of the screen. Viewport coordinates are normalized 0 to 1. 3. Physics.raycast, ray, outhit, 100f, performs a raycast. Asterisk ray, the ray to cast. Asterisk out hit, a raycast hit structure that will contain information about what the ray hit, if anything. Asterisk 100F, the maximum distance the raycast will travel. 4 if, physics.raycast, checks if the raycast hit anything. 5 aim target. Position equals hit. Point, sets the position of the aim target, example your reticle, to the point where the ray hit the object. 6 transform. Look at, hit. Point, rotates the character to look at the hit point. How to use asterisk. 1. Create a 3D object, example a cube, in your scene. 2. Create a camera in your scene. 3. Attach the raycast aim controller script to the cube. 4. In the inspector for the cube. Asterisk drag the camera from the hierarchy into the player camera field. Asterisk drag the camera from the hierarchy into the camera pivot field. Asterisk create a new 3D object, example a sphere. This will be your aim target. Asterisk drag the sphere from the hierarchy into the aim target field of the raycast aim controller script. 5. Create some other 3D objects in your scene for the raycast to hit, example a plane. 6. Run the scene. When you press the aim button, the character should now aim towards the mouse cursor, and the aim target should move to the point where the raycast hits. Part 5, Advanced Considerations and Customization. Asterisk input buffering and queuing. Asterisk for fast-paced games, you might want to buffer or queue input. This involves storing input events and processing them over multiple frames to avoid missed inputs. The input system has built-in mechanisms for this. Asterisk action phase control, started, performed, cancelled. The input system provides 3 phases for each action, started, performed, and cancelled. You can subscribe to events for each phase to trigger different behaviors. For example, asterisk input context. Asterisk the input action. Callback context passed to the event handlers provides valuable information about the input event, such as the device used, the time the event occurred, and the raw input value. Asterisk custom input processors. Asterisk you can create custom input processors to modify the raw input values before they are used. For example, you could create a processor to smooth the input from a gamepad joystick or to apply a custom acceleration curve. Asterisk different camera types. Asterisk experiment with different camera setups, example first person, top down, fixed camera, to suit your game's needs. Asterisk aim assist. Asterisk implement aim assist features, example slight rotation correction when the crosshair is near a target, to make aiming easier for players, especially on consoles. Asterisk animations. Asterisk integrate animations into your aim controller. Transition to an aiming animation state when the aim button is pressed and blend back when it's released. Asterisk character controller integration. Asterisk when using Unity's character controller, ensure that your aiming rotations don't interfere with the character's movement. You might need to temporarily disable movement input while aiming or adjust the movement calculations. Asterisk sensitivity curves. Asterisk apply sensitivity curves to the input to provide finer control at low speeds and faster movement at high speeds. This can significantly improve the feel of aiming. Asterisk recoil. Asterisk add recoil effects when firing weapons to make them feel more impactful. This could involve temporarily offsetting the camera or the weapon model. Asterisk weapon sway. Asterisk simulate weapon sway to make the aiming feel more realistic. This could involve small, random rotations of the weapon model. Code example, smoothing input. In this example, vector 2.smooth damp is used to smooth the look input over time, resulting in a less jerky aiming experience. Part 6, Troubleshooting. Asterisk input system not working. Asterisk make sure the input system package is installed and enabled. Check that the input action asset is correctly configured and that the action maps are enabled when needed. Asterisk no input received. Asterisk verify that the bindings in your input action asset are correct and that the input controls are working properly. Use debug.log to print the input values to the console. Asterisk rotations too fast or too slow. Asterisk adjust the rotation speed and look sensitivity variables in the inspector. Asterisk camera issues. Asterisk double check that you have assigned the camera component to the player camera variable and that the camera is positioned correctly in the scene. Asterisk raycast not hitting. Asterisk ensure that the raycast is originating from the correct position and direction and that the objects you expect it to hit have colliders. Use debug.drawRay to visualize the raycast in the scene. Asterisk script execution order issues. Check the script execution order settings in Unity if scripts are not executing in the expected sequence. This comprehensive guide should provide you with a solid foundation for creating sophisticated aim controller systems in Unity using the input system. Experiment, iterate, and adapt these techniques to create the perfect aiming experience for your game. Remember to consult the Unity documentation and online resources for further details and advanced features. Good luck.